Hello class, welcome to MEM4225, Advanced Products and Processes. Module 1, Queuing Systems and Manufacturing Simulation. Part 1, Background.
My name is Liang Zhang. I'm Associate Professor of Electrical and Computer Engineering. I'm also affiliated with the Management and Engineering for Manufacturing program at UConn. My email is liang.zhang@uconn.edu and my office is IT333. In this module, we'll first start with introduction and background to give you an overview of what this module is about, the problems we address, and the systems that we'll focus on. Then in the second part of this module, we'll discuss fundamental theory of queuing systems. And the goal is to help you learn the exact mathematical formulas to calculate performance metrics of simple queuing systems. Next, with the theoretical knowledge of queuing systems, we'll learn how to use a commercial professional simulation software called Simulate to construct simulation model of those fundamental basic queuing systems. And the goal is such that you can use the software to build, set up, run, and verify the simulation models of those systems by comparing the output of the simulation model and the metrics calculated using the formulas. After we're familiar with the simulation software, we'll go ahead and discuss how to use that particular software to analyze production systems. And the goal again is to use this simulation software build, set up, and runs the production system models and analyze the output data. Now, since this module is on manufacturing systems, we'll start by discussing the 6 general ideas or general areas of manufacturing. And of course, this is only one way to categorize the entire field of manufacturing. In our view, we first start with materials and products. Right? These two things compose the basic fundamental components in manufacturing processes. And in the past few modules, in the other modules, you have learned material and knowledge and tools related to analyzing various properties and phenomena related to materials and products. Machine tools, material handling devices, are the components that will handle and process the materials and products and eventually make them into final goods. As soon as we figured out the process to make those products, we'll have to arrange the set of machines, equipment, material handling devices, usually viewed as buffers, as well as human laborers around them, so that the desired products can be produced in the most efficient and effective manner. This is what we call production systems. In a higher level, to deal with various demands from the market, from the downstream customers, we also have to plan and schedule the production activities. So this is the fourth area. And the main problem here is to optimize various activities along with the consideration of time, cost, quality, and so on. Mentioning quality, the assurance of quality is a major problem in the entire manufacturing systems research and practice. The main tool here is called the Statistical Process Control, SPC, and there are various mathematical tools and qualitative tools, graphical tools developed in this area. And finally, the sixth area is what we call work systems. And the goal is to look at how to train and pay workers, operators, so that they optimize the system enterprise performance through their own interest. Now, this particular lecture focuses on the third area, production systems. In other words, we've figured out the set of machines and material handling devices. We know how to deal with the material and products. Now we will put them into a system and analyze the performance as a system. Production system itself is not a new field. It has been analyzed or studied extensively for several decades. And there are various tools developed. For instance, people talk about lean manufacturing. Just in time from Toyota, and then overall as a Toyota production system, TPS. People talk about Six Sigma, theory of constraints, push production, pull production, and so on and so forth. There are various terminologies introduced in various categories in various fields or directions or branches of the study. But what they are, well, I took some definitions from Wikipedia to help us understand what these tools are about. For instance, lean manufacturing is defined as a production practice that considers expenditure of resources or any goal other than creation of value at the end of the customer. Of course, the goal here of lean manufacturing is to reduce waste, and the waste can be in different areas. It can be the waiting time, can be the idling of machines, could be the time you try to search for a particular tool, transportation from one spot to another spot in the facility, and so on. Just in time is a production strategy that strives to improve business return on investment by reducing in-process inventory and associated carrying cost. It's apparently relevant to lean manufacturing, and just in time means we want to reduce again the waste, in this case time. In TPS, Toyota Production System is an integrated social technical system developed in Toyota that comprises management philosophy and practices. And finally, Six Sigma is a business management strategy. It was first developed by Motorola in the 80s. Now, in this slide, I've highlighted or put those words in bold to emphasize what I'm trying to say here. So if you look at these tools, Lean, Just-in-Time, TPS, and Six Sigma, they are practice, strategy, philosophy. And these words can help us in a qualitative manner to improve the manufacturing process overall. However, we do need more quantitative tools, more rigorously defined engineering tools to push the boundary. Now, theory of constraints is also a popular tool in manufacturing practice. It's an overall management philosophy introduced in one of the best-selling books, The Goal, which is geared to help organizations continuously to achieve their goals. As we can see from this picture, it's sold over 3 million copies, and almost every manager on the factory floor owns this book, and it's also being used as one of the textbooks in a lot of business schools in this area. But again, this book is mostly focused on intuitive and common sense tools that can help, or methods that can help improve the manufacturing process, but not to the level of rigor that typical engineering would require. And the goal of this module is to provide you such quantitative goals through what we call computer simulation of production systems. Now, when we look at overall system, no matter it's production system or any other system, the investigation can usually be done in two ways. First, we can experiment with the actual system, but this can become costly, disruptive, and may not be appropriate for certain scenarios or applications. So if that's the case, we sometimes can experiment with the model of the system. But there's always a question of whether or not the model you created can actually reflect the nature of the system or the essential nature of the system you're focusing on. In terms of the model, there are two different types of models we can work with. Or one is a physical model, meaning you can build a tabletop scaled model of the actual system. Right? It can be, for instance, 1 to 24 or 1 to 1000. A smaller scale physical model can sometimes help you understand some of the basic features of the actual system. And you can do the simulation based on the actual tabletop model or scaled down model. The other type of model is kind of the mathematical model. Of course, that means you will have a set of mathematical equations, formulas, and the intrinsic Interactions of the components in the system are characterized by those equations and formulas. And when you do that, of course, you have to make a bunch of assumptions that will take the form of mathematical or logical relationships. And whether or not those assumptions are valid is a critical problem to solve when we build a mathematical model of a system. And when we have the mathematical model at hand, there are two approaches still to approach a mathematical model or to study this mathematical model. One is to rely on the mathematics and derive analytical solutions. Well, if the model is simple enough, we can apply our mathematical tools like calculus, algebra, probability theory, statistics to derive those equations or solutions. But this may not always be the case. When the system becomes more complex, we have to use computers, and particularly we can use simulations to help us mimic the actual operation of the system through the mathematical model. In this module, the computer software we'll use is called Simulate. It's professional simulation software as used to model systems with this queuing phenomenon. Student versions are available for download, and the downloading information will be posted on Husky City through course announcement.